Okay, I think we can make a start. Welcome to the BGP Techniques for Internet Service Providers tutorial. This is, well, the next in an ongoing long series of BGP tutorials that I've been doing for the NANOG community, the various NANOGs, over the last few years. So this one is for, again, it's a fairly basic BGP introduction, slanted more towards internet service providers than any other users of BGP. My name is Philip Smith. I work for Cisco Systems. Spend probably about half of my life in airplanes traveling around the world, going to various operator group meetings and so forth. So again, I'm very grateful to the NANOG program committee for inviting me back for another stint here. So the presentation slides are there. They're also on the NANOG website. I think if you check the NANOG website right now, you'll get the most up-to-date slides. I was a bit bad and I made one or two last-minute changes on the plane from London yesterday, and well, I think Susan was very happy about that. But there are, if you downloaded the slides in the last few days, they were updated about an hour ago, so you can get them from either of those locations. Also, please feel free to ask questions at any time. If you do want to ask questions, can you please use the microphone that's positioned in the middle of the room? Because the presentation is being recorded. It's just so that the questions can be heard, not that the answers are just appearing with no obvious reason for them. So if you please use the microphone in the middle of the room, that would be much appreciated. If you don't want to ask questions during the presentation, you can ask during the break or any time the next 2 days, or send me email, whatever. So this is basically what we're going to look at this afternoon. There are two 90-minute presentations. I should get most of the first two bullets covered in the first section, and the final two bullets will be covered in the second section after the break. And I'm not going to try and aim for any particular target in the slides. It's just what we don't get finished in the first 90 minutes we'll complete in the second. The first bit we're going to look at is hopefully just a recap for most of you. To have a look at some of the what I call BGP basics. What is BGP? Well, it is a routing protocol which is used to exchange routing information between networks. Very, very simple definition. It's what's called an exterior gateway protocol. In other words, a routing protocol that runs between exterior systems in a network, or devices that face different networks. For example, you may be one service provider, you have a device that speaks to some other service provider. That process is an exterior gateway protocol. BGP is described in RFC 1771. That's actually now quite an old RFC, and there's been a lot of work going on within the IDR working group over, I suppose it's almost recent years, to update the BGP spec to actually match what's happening in the real internet today. The current draft is that one. It's iteration 23. I imagine it's very, very soon going to appear with its own real RFC number, but that's the current draft. BGP uses what's called an autonomous system. An autonomous system is BGP's fundamental operating unit. And an autonomous system is used to uniquely identify networks with a common routing policy. So what's an AS, or autonomous system? It's basically your network. I mean, you have a network with routers in it. Your collection of routers in your network is your autonomous system. I mean, that's, you're using a single routing protocol on that network. You own it all, you trust everything that's in there, you control everything that's on there. You usually find the autonomous system is a one-to-one correspondence with your own network. Not always the case. You find sometimes the ASs will span more than one, what you consider an identifiable operating network, but that's quite a rare instance. Now, with all these people having these autonomous systems, how do we actually identify them? Well, an AS has a unique number. Okay, that number is unique in the internet. It's called the autonomous system number. It's a 16-bit integer. There are 64,511 of those available for public use, in other words, use on the internet. There are about 1,023 which are available for private use and should never appear on the internet. So they can be used within your own network, for networks not connected to the internet, or whatever. AS numbers 0 and 65535, of course, are reserved. 32-bit AS numbers are coming soon. There's a bit of, well, has been a bit of, I wouldn't say panic, but a bit of worry or concern about the rate of consumption of AS numbers with the growth of the internet over the last few years. So the ASNs have been extended from 16-bit to support 32 bits, according to that internet draft. So it's at the 8th iteration, and again, I imagine very soon it will become its own RFC. ASN 23456 has been reserved for the transition process, whatever that transition process is going to be. I don't think it has been exactly defined yet. But when we do run out of 16-bit AS numbers, we will have 32-bit numbers, and we'll be able to move over to them at some stage in some process. Where do you get them from? Well, AS numbers are distributed by the regional internet registries. There are 4 regional internet registries serving geographically large parts of the world. You can also get AS numbers from your upstream ISPs, if they're a member of one of the RARs. Current AS allocations have been made up to 32,767. So that's been handed out from the IANA to the regional internet registries, and the regional internet registries in the process of handing those AS numbers out to the ISPs who qualify them. So, as I say, the numbers that have been handed out from IANA are 32,767, but of those we only see about 17,000 on the internet, depending on where you look. But there are approximately 17,000 in visible use on the internet. So there have been many thoughts, studies, and so forth as to where the other 15,000 have disappeared to. Not our worry for here, though. Now, how does BGP work? Well, the first thing to bear in mind is BGP runs over TCP. Okay, it uses port 179. So I do a lot of training like this. I do a lot of workshops, ISP security, and this type of thing. And one of the classic mistakes that newcomers make is they set up very secure filters on the edge of the network, and they can't bring BGP up. Or they bring the BGP session down because they actually end up filtering port 179. You need to allow TCP 179 connections between you and your neighboring routers. Otherwise, you won't get BGP. It's a path vector protocol. We'll talk about that. It relies on incremental updates. Why that? Well, in a nutshell, the current internet routing table is about 138,000 prefixes today. Trying to send all that information as one big update would probably take several minutes, depending on your hardware and your network bandwidth. So BGP will only tell its neighbors about changes that have happened in the network. And the final point is there are 2 types of BGP. Even though there's only one BGP that we're going to be talking about, there are actually 2 instances where it can be used. The first one is internal BGP. The second one is external. I'm just looking at the diagram there. Routers A and router C would carry out something called peering, and that is the activity of talking BGP with each other. In other words, exchanging routing information. So you see the general scenario. We've got the ASs, the individual networks, AS100, AS101, AS102. They've got connections of some description to each other, whether it's a point-to-point link or whether it's some shared media as between routers B, D, and E there. And we will talk BGP between these ASs across that media. Now, those parts of the network, the bits of the network that are outside yours, are used to connect to other service providers, are what's called the demarcation zone. Well, people have got various names for it, but the most common I've seen used is the demarcation zone. And that's the shared network between ASs. So that might be a circuit that you and your neighbor jointly own, or you own it completely, or it might be an Ethernet switch where several different providers are present and will connect to. Now, the way BGP works is by basically learning multiple paths for internal and external BGP speakers. It will pick the best path somehow through some mechanism, which we'll talk about in a bit, and will put that best path in the forwarding table. This best path is also sent to external BGP neighbors, and you can actually influence how this best path selection process works by applying policies. So there's actually quite a lot of content in these 4 simple points on the slide. There's quite a lot of content, and it forms the bulk of the next 30 or 40 slides of the presentation. Okay? So the policies is actually quite an important part. It lets BGP control what's sent, or what lets you control what is sent between you and your neighbors. So firstly, eBGP and iBGP. Well, eBGP is used externally. eBGP is used to exchange prefixes with other ASs. It's external, it's a BGP that runs outside your network between external facing routers. And that is where you implement your routing policy. Whereas iBGP is used internally, it's used inside your network. And it's used inside your network to carry some or all of the internet prefixes across the ISP backbone. Not only is it used for that, it's also used to carry your own customer prefixes, because what you carry within your own backbone is quite often different from what you tell other people about, as we'll see in the slides later on. So there are 2 BGPs, there's the eBGP and there's iBGP. And this is a model representation. I thought I would draw a picture of how it actually all works, because people sometimes have trouble visualizing how this is meant to go. I'm assuming that you all know what an IGP is. It's an internal routing protocol. It can be OSPF or ISIS. Those are the 2 that are commonly used in the internet. And your internal routing protocol, such as OSPF and ISIS, is used simply for letting your routers talk to each other so they know where they are. Whereas BGP is used for carrying what I basically call the content. It carries the full internet routing table, or your customer of networks, and any other address space that you need to push around your backbone. So I see it more as iBGP carries the weight across the backbone, and eBGP is the thing that moves the prefixes you want to send from your network to other networks. Now let's look at external BGP. eBGP runs between BGP speakers in different ASs. So simple example here. These BGP speakers need to be directly connected, so physically connected to each other. Some people try and work around this by saying, oh wow, man, I can just run OSPF between AS100 and AS101. That way my eBGP speakers don't need to be directly connected. It will work quite nicely that way. And then, well, certainly in my day, when I was working at an ISP, we had wonderful examples of OSPF from our customers bleeding into the OSPF from somebody else's network and so forth. You really do not want to run an internal routing protocol on an external network. It's called an IGP for a reason. But you'd be amazed the number of people who really still want to try and run an IGP on an external part of the network. So routers A, B, and C need to be directly connected with each other. They've got no way of knowing how to reach each other unless they are on a connected network. Internal BGP is slightly different. Here the BGP peer is within the same autonomous system. And you're not required to be directly connected here, because what you have an internal routing protocol running within your own network remember us saying the IGP was there to let your routers know how to get to each other. So if your routers know how to get to each other with IGP, you can relax the rules for internal BGP and simply let IBGP deal with carrying all the prefixes roundabout. IBGP speakers also need to be fully meshed, because all the IBGP does is originate connected networks, and they take prefixes that they've learned from outside the IBGP or outside the local autonomous system and pass them around the IBGP. IBGP will not pass on prefixes learned by other IBGP speakers. Now, this originally was a design thing to try and avoid getting routing loops. But as we'll see later on, it's actually a bit of a problem for scaling IBGP to large networks. But take it at this stage, IBGP speakers need to be fully meshed. Okay, IBGP peering is generally topology independent. Your IBGP speakers do not care at all what your network looks like, how the routers are connected to each other, and so forth. IGP takes care of that. Okay, so we could have a situation like, well, routers A, B, and D will talk IBGP to each other, but A and D are not physically connected to each other. You actually go through router C. And again, doing workshops, we set up fairly, well, I wouldn't say they're complicated, but they're reasonably sophisticated classroom exercises for students to do. And people are quite happy to accept the eBGP directly connected thing, but then when we're setting up IBGP, it happens about 70–80% of the class will set up an IBGP with only physically connected neighbors. They miss the point that you can actually set up IBGP with any router within your autonomous system. So even I just put it up on the slide here and it looks nice and easy, but when it comes to implementation, even though I've given these various slides to students, they still don't quite get the concept. Okay, it's quite important. IBGP needs to talk to all other IBGP speakers. Okay. Another important thing to try and do with IBGP is to peer with a loopback address, or at least some interface on the router that is always there. The handy thing with a loopback is, well, it doesn't go down. It doesn't ever go down. It's always there. You can't unplug it. You can't pull it out of the box. You can't delete it, at least not without really a lot of hard work. Whereas any of the physical interfaces like Ethernet or serial or so forth, Ethernets can go down, serial interfaces can go down, connections can break and so forth. So if your IBGP peering is between the loopback on the router, then the chances of that going down are fairly remote. For example, if you look at the picture I have here, if we set up the IBGP session between the physical connection, say on the two routers on the right-hand side, that would all be fine. What happens if that serial link goes down? The IBGP session would go down because the next hop's not there. If the IBGP session goes down, the prefix is learned by one IBGP router from the outside will not get passed to the other IBGP router that is talking to. So you get disconnectivity in the network, and your customers start phoning up and complaining, "Ooh, well, your internet connection's broken, ooh," and all the rest, just because one of your backbone links has vanished. Whereas if you set up the IBGP between the loopbacks, well, OSPF will take care of how you get to your loopback. Okay? If the serial link on the right breaks, your IGP will reroute via the other router on the left-hand side, and then you have maintained connectivity that way. So you can actually bring down bits of your backbone, and IBGP won't actually see any difference. Okay, so it's quite important that IBGP stays stable all the time. You don't get disconnectivity in your backbone or any other problems. It's quite interesting. I've seen many ISPs who run IBGP between physical interfaces and the router, but they've got very, very stable infrastructure and they don't have any problems. And I mean, I live in Australia, I work in Asia Pacific region. There the infrastructure is not half as good in places as it is here. And I've seen people run very, very stable IBGP sessions across a network infrastructure that's really, well, I wouldn't say it's chronic, but it's pretty bad way. and they can maintain very, very stable iBGP sessions simply because OSPF is doing the work of making sure that the iBGP routers are still talking to each other. So from the customer point of view, because IGP is rerouting very, very quickly, the network is working very, very well, even though the actual physical infrastructure is giving the ISP a bit of a headache. Okay, so this is quite an important thing. Now, BGP has what are called attributes. And attributes, well, I've subtitled it as information about BGP, but actually as a means of letting you apply a little bit of policy. Okay, the attributes are information about the prefix that is being carried by the BGP process, and this extra information, if you like, can be used to apply policies when you share prefixes with other ISPs. So let's have a look at some of them. Well, the AS path is the first one I want to look at, and it's actually quite an important attribute. The AS path stores the sequence of ASs that a route has traversed. So for example, if a prefix is originated in AS100, say 180.10/16, we announce that to AS200, and then we take a look on AS500 and one of the routers there. Well, we see 180.10/16, and then we see this list of numbers, 300, 200, 100. Those numbers are the list of autonomous systems that the prefix has visited. Okay, so the leftmost one is 300, that is, well, the autonomous system that I heard the prefix from. 200 is the one that 300 heard it from, and 100 is the one that 200 heard it from. Now 100 is on the extreme right, therefore 100 is the autonomous system which actually originated this prefix. Okay, which is, if you look at my little diagram, is what happened. Okay, and that is called the AS path. It's the list of ASs that the prefix has traversed. Now, why do we have the AS path? Well, yes, to apply policy, to provide information where the prefix came from, so we know that what the origin AS was. It's also there for loop detection, as we'll see in the next slide. Okay, if AS500 has a connection back to AS100, for example, well, we take 180.10/16, we have a peering with AS100, we send them the 180.10/16 prefix, and then AS100 router says, this is interesting, 180.10/16, I've heard it from AS500, and I've heard it from this router locally as well. It's heard it from two different places. And so on. And potentially you can have AS100 send a prefix to 200, and it goes round and round in circles, and you have a never-ending loop. That's a possibility. Okay. Now the whole point of having the AS path is we don't want autonomous systems to announce our own prefixes back at us. I mean, we originated them, so they should come back at us. So again, depending on how the implementation is in the different autonomous systems and the routers, AS500 may detect that it's peering with AS100, so just not send this prefix back to the AS that originated it. And AS100 most definitely will spot anything that was originated by it coming in from the outside. And that way we avoid having any routing loops. Now the next attribute is the next hop. And the next hop is basically the IP address of the router that sent us the prefix announcement. So for example, router A is sending 150.10/16 network, and it sends it to router B. So router B sees 150.10/16 with a next hop address of 150.10.1.1. It's the router I heard it from. Okay, that's the next hop address. That's for eBGP. Now, iBGP, we don't go and rewrite the next hop. So router B will take this prefix, pass it on to router C, and it will maintain the next hop. The next hop will not be changed. The reasoning there being that, well, this is actually the external address we use to get to this prefix that's outside our network. How do we get to 150.10.1.1 from router C? Well, BGP doesn't care, because the ISP has implemented an internal routing protocol to take care of that. And again, it's one of the deployment things that people run into with deploying BGP for the first time, or even deploying anything more than static routing. They forget about the next hops. So they'll be quite happily setting up eBGP to the neighbor. They set up iBGP, say, to router C, but they forget to carry the point-to-point link address in OSPF, for example, so that router C actually knows how to get to the next hop that comes with the BGP prefix. Again, putting it on the slide here, it's very, very easy. People say, yeah, okay, it's fine, I'll remember all that. And this is like, I think it's number one or number two classic standard mistake that people will make. Not having the external next hop address somehow reachable from inside your own network. Okay, so that was the second attribute. For iBGP, just taking a closer look at how the next hop is. If you inject a prefix into BGP inside your own network, say it could be from a customer, you want to put it into your iBGP because you're going to announce it to somewhere else, possibly. Well, the next hop address that's used by the router that installs this in your BGP table is, well, basically the loopback address of the router. If you're running your iBGP between the loopbacks, that IP address will be used as the origin, which is quite handy because you've now got all your prefixes learned by your neighbors pointing to next hops that are independent of the infrastructure of your network. So if you didn't peer between loopback interfaces on your router for iBGP, if you peer between physical interfaces, then your next hop address might be a physical interface. And if any interfaces go down, you could really end up messing up your customers or worse within your own backbone. So this provides a level of useful abstractness for iBGP. And of course, you use OSPF to figure out how to get to all your next hops. Using OSPF is what I've called the recursive route lookup. Okay? Because OSPF will know how to get to loopbacks via the various routers within your own backbone. So, summary about the next hops. IGP should carry the route to the next hops. We're using something called recursive route lookup. So, BGP points to the next hop, which is known via OSPF, and OSPF figures out how to get to that particular next hop. The important thing is it unlinks BGP from the actual physical topology. And part of all this is you want a stable internal BGP implementation in your network. And it lets the IGP make the intelligent forwarding decision. And it really pains me sometimes to watch people trying to fine-tune BGP so much that it does the 30 milliseconds failover that OSPF and ISIs are probably more suitable for doing. I mean, OSPF and ISIs could do all these really rapid failovers. BGP is not really intended to be a rapidly changing thing. It's trying to carry on there to maintain stability within the actual internet and your own internal network. So let IGP make the intelligent forwarding decision. Okay, origin. This is, well, I don't want to be rude about the origin, but I would say it's pretty much a useless attribute. I don't really know anybody who makes much use of origin anymore these days. I mean, I've been very polite and I've just said historical attribute because it was used a long time ago, and I, quite frankly, don't see much use of it these days. Conveys the origin of the prefix, but it's not the name of the system or anything like that. It's which routing protocol it came from. And just to confuse things a little bit more, IGP there does not refer to OSPF. That's what I kind of really dislike giving this slide, because certainly to newcomers, because we've taught them OSPF and they said, yeah, OSPF ISIs, that's an IGP. And then they get this IGP, does that mean you take OSPF routes and put them into BGP? And it's like, no, not that, definitely not that. Okay. IGP means it's come from a BGP. It's been put in there by a BGP network statement. In other words, BGP has originated the prefix into the routing table. EGP means it has come from the old routing protocol before BGP called EGP. Okay, as I say, I don't think many people are using EGP anymore these days. And this origin thing was there really to allow for the transition between EGP and BGP. When we come to the BGP path selection process, you'll see that prefixes originated from BGP are preferred over prefixes originated by EGP, which are preferred over prefixes originated from somewhere else. Okay, so that allowed a transition from EGP to BGP. So the three possible values for origin, I don't see anybody paying any attention to them anymore these days, so I think I should just move on. Aggregator, it conveys the IP address of the router or BGP speaker generating the aggregate route. So it's actually very useful for debugging purposes because you can actually see where the aggregate was generated, well, the IP address of the router that generated it. But apart from that, not a great deal of use that I've seen. I mean, it's not used in the path selection process, simply used for providing information. Now, not the first, I suppose, the second of the really, really useful attributes. AS path is a very useful one. Local preference is the second really useful attribute. Now, we've looked at simple situations in the introductory part. What happens when your network's connected like this? You've got AS400. There's got two possible ways to get to AS100. Okay, you can go AS400 to 200 to 100. You can go 400, 300 to 100. Which one do you choose? I mean, you can take a coin out and toss the coin as it heads or tails, but routers don't really have very good facilities for doing that sort of decision process. So we have something called local preference. AS100 is originating 160.10/16 network. He sends it to AS200, and he sends it to AS300. 200 and 300, like good ASs they are, they pass them on to AS400, and router C, sitting at the bottom there, sees two possible paths. He can get through router A, he can get through router B. Which one should he choose? Well, rather than having just some random event, that's what's kind of hinting at with tossing the coin, rather than just having some random event decide how traffic should go out of your network, you can use local preference. Okay, the prefixes come in from router D and router E. You can set a preference on which outbound path you want your traffic to take. Okay. Now, for local preference, it's the highest value that wins. So if we set local preference at 500 on router A and 800 on router B for this particular prefix, then 800 is bigger than 500, so the path through router B to router E is chosen for outbound traffic to get to 160.10/16 network. Okay, so that's local preference. It's actually the most powerful attribute there. Again, when we come to the path selection process, you see that local preference is basically number one. It means that you can override anything and anything else that somebody sends you. If somebody says, I want your traffic to use this way, well, you can accept that if you want. You can override it, and you can use local preference to do that. Okay, so local preference gives you the ultimate control over how traffic exits your network. So it is a very powerful attribute. Okay, it's local to an autonomous system. So if you set a local preference on a prefix within your network, and then you announce that prefix to somebody else, well, the local preference will not be sent. Okay, your neighbor will pick up the prefix and he'll attach his own default local preference to it. Okay, most implementations use default local preference of 100. Some people will change the default local preference within their network for their own purposes. Okay, it determines the best path for outbound traffic. Okay, routing announcements come in, traffic goes out. Again, that confuses a lot of people as they're learning this, how internet routing actually works. Routing information flows in one direction, traffic will flow in the opposite direction. So routing information coming in, we set local preference on to determine how traffic will flow out. And the highest local preference wins. Now, the partner, I suppose, for local preference is multi-exit discriminator, or MED. Most people will call them MEDs. People who've been in the industry far too long, we'll probably still call them metrics, because that's what we used to call them with, I think it was BGP 3, we called them metrics. But they've now got the, I suppose, proper name, meds, and they're used for the opposite purpose. You will send somebody a med to determine how traffic flows into your network. Okay, so med is an outbound information thing. For example, you're originating 192.68.1/24 in AS201, you're sending it to router C in AS200, and you want traffic to come in one particular path. And how you do that is you use an MED to do so. For example, on router B, you set an MED of 1000, on router A, you set an MED of 2000 in the outbound announcement. So router C sees two possible paths, one with an MED of 1000, the other one with an MED of 2000. Just to confuse things, the lowest MED wins. Okay, it's a bit like internal routing protocols where the lowest metric wins. That's how I try and remember it, and that's how I try and ask other people to remember it, and sometimes they generally do. But quite often, we end up with people thinking lowest local preference wins and highest metric wins. So it's just a case of having to learn it, memorize it, and get used to it. Okay, so lowest MED wins. So in this case, MED of 1000 is lower than 2000, so traffic coming in from AS200 for that network will go from router C to router B. Okay. MED is also a non-transitive attribute, and it's also an optional attribute. You find that some BGP implementations don't actually use MEDs at all. So it's used to convey the relative preference of entry points, determines best path for inbound traffic. Just to help with the confusion a little bit more, it's comparable only if paths are from the same AS. So it helps in that situation. In other words, we've got parallel paths from the same AS. So it's quite often used between neighboring ASs where there are multiple connections, and you can help trying to do the load sharing between you and your neighboring network. But some implementations have an option to relax this rule. Okay? You may be trying to compare meds between you and some other autonomous system, but transiting different ASs in the middle. Some people have had that need, so they've gone to their favorite vendors and said, we need this, can you please add a knob? And so the knobs begin. Path of lowest MED wins. Absence of an MED attribute implies an MED value of 0. Okay, and that's in the current BGP draft. Danny McPherson has written quite a nice internet draft that I've referenced at the bottom there, showing some of the possible MED confusions. In fact, there are quite a few people who just really dislike using MEDs at all these days because different vendors have implemented them in different ways, there have been different defaults, there have been, and so on. So I've just tried to list some of it there. Some implementations send learned MEDs to IBGP peers by default, others don't. Some send MEDs to eBGP peers by default, others don't. Default metric value varies according to vendor implementation. The original BGP spec made no recommendation. So some implementations said no metric was equivalent to 2 to the power 32 minus 1, or others said it was 2 to the power 32 minus 2 because some people use 2 to the power 32 minus 1 as an unreachable route. Another implementation said no metric was equivalent to 0. And if you put two of these implementations together, you could end up with wonderful routing loops. Okay, as one thought one way was the best, another one said it was the worst possible case. So because of this, you've really got to know what your neighboring peer is using, what the implementation says is default and what isn't default, and so forth. So I've said potential for metric confusion, which is being very kind. I mean, I think if you read Danny's draft, you get a better idea of some of the considerations that you need to make when using MEDs. Put it this way, not many people use MEDs anymore, and they will use BGP communities, which I'm going to talk about in a bit. Like this. Okay. Communities are described in RFC 1997. It's a transitive attribute, and it's also an optional attribute. It's a 32-bit integer, but because humans aren't very good with 32-bit integers, It's got a nice friendly format as used in RFC 1997 and 1998, which is your local AS number, colon, and then a number between 1 and 65,000, whatever, which you can use for your own uses, which you can specify yourself. There's some reserved communities, so the first and last 65,000 communities are reserved. Communities are used to group destinations. Okay, so they're used to group prefixes, if you like. And prefixes can belong to any number of communities. It's not like ASs where generally a prefix belongs to only one AS. Communities can have any number of prefixes. A prefix can belong to any number of communities. And I've said they're very useful when applying policies within and between ASs. And again, that's huge understatement. They're massively useful. Towards the end of the presentation, probably middle of towards the end, I'm going to show you some examples from some ISPs of how they use communities to help their customers talk BGP to them, load share with them, and so forth. And communities are so extremely powerful. I mean, I go back to my days at UUNet, and when communities first appeared in iOS, I mean, we tried them out very, very early on, and we moved a pile of policy and so forth within our own network through massive and horrible access lists into communities. I mean, it was about a 3 or 4 month job to actually migrate all this stuff, and my engineering team did all that, and it was quite extraordinary simplification on the actual network and network operation that communities made. So if any of you are running a network today using BGP, haven't really looked at communities or what they are, then I'd really strongly encourage you to do that, because the administrative ease that it converts your network to is quite amazing. Okay, here's an example. This is how it's all made easier. Got an ISP in AS300. Got a few routers there. He's got some customers. He also has a connection to ISP number 2. So what have we got? Well, we've got AS100 connecting to AS300. He's originating 160.10/16. Router B in AS200 is originating 170.10/16. So they're customers. So we connect to router C, they talk BGP with each other, and we say, okay, we'll put those in community 300:1. Note the 300 there is my AS number, AS300. You don't have to use your own AS number, but the internet convention is that any communities you set for your own use, you put your own AS number there, and then the second number after the colon you just make up as you wish. Okay, so these customers, AS100 and AS200, go into community 300:1. IBGP across my network. Router E is talking to another of my customers, or maybe it's a peer or something, it doesn't really matter. And router E is only going to announce my customer prefixes to AS400. Okay, so we just have a simple filter that says any member of community 300:1 I'll send to AS400. Now, I've also got a connection to this ISP2 who is announcing 200.10/16. Because he's not a customer of mine, I put him in community 300:9, which means something else. It could be ISP peer. And because router E is only sending prefixes belonging to community 300:1 to AS400, that's all that goes. AS400 will not be able to see ISP2 through this connection. Okay, now that's using communities. Now how would you do this if you weren't using communities? Well, on router C you'd have a filter that says, on the BGP session with router A, that says, only allow 160.10/16. And router C with B, only allow 170.10/16. So you've got those filters. That's fine, that's easy. Router E, okay, we need to set up a filter that says only allow prefix 160.10/16 and 170.10/16. And you say, well, yeah, that's okay too. You've had to do 2 filters. What happens when AS100 now wants to add another prefix? Well, you then have to go and update your filter on router C, and you've got to go and update your filter on router E. And certainly in the days before communities appeared, we didn't have any other fancy tools that let us adjust the policy on BGP without tearing down the whole BGP session. So if you look back to like 94, 95, to change any policy, we had to shut down the BGP and then bring it all up again. And that caused several minutes disruption on the network. It was painful. So when communities appeared, you see all the difference it makes. If AS100 adds another prefix, he just starts announcing the prefix because the filter on router C will automatically tag on the community 300:1. And the filter on router E is completely unchanged. You don't have to touch it. So you don't have to bring down your BGP sessions at all. Okay, it was nice and simple. And so I think you can see why we sort of dumped all the old stuff that we did and went straight for communities. It meant that, well, it basically meant before, if we got a new BGP customer or they wanted to announce another prefix to us, we could only announce that prefix to our BGP neighbors during our maintenance slots. So we get a customer who adds a new prefix on Friday and we say, sorry, you're going to have to wait till Tuesday, 4 in the morning. And well, a lot of people didn't really like that. It's like, well, I'm announcing this prefix to you now. I want you to announce it now. I'm paying you money, damn it. So with communities, we didn't care what they did. They could announce it at 5 to midnight on Friday. It would appear on the internet immediately. And with the right community and all the right filters set. Okay, it made such a big difference. Okay, I'm going to do communities to death more as we go through the presentation, but I hope that gives you some introduction as to how they work. They really are fantastically useful. There's some well-known communities. These are the 4 of them. I've put in the URL of where IANA have listed the well-known communities. I don't know if this, well, last time I looked, this wasn't actually public, but I think they may well have fixed it in the last week or so. The 4 of them, there's no export, which means do not advertise this prefix to any eBGP peers. There's no advertise, which means do not advertise to any BGP peer at all. And there's no export subconfed, or no local AS, local AS, which means only advertise it within the local AS. And that's used for BGP confederations, which I'll cover later on. And the final one, which is the newest one, is no peer, which means do not advertise to bilateral peers, and that's written up in RFC 3765. So that's the most recent one that has appeared. So those are the well-known communities. So how does the no export community work? Well, it's most useful in this sort of situation. You've got multiple links to, I don't know, a neighboring ISP, your upstream ISP, whatever, and the standard way of load sharing over multiple links is to take your address space and subdivide it. Okay, you may have 170.10/16. If you subdivide the address space equally over those links, then you could hopefully load share equally across those links. The trouble is, if you subdivide your address space to your upstream ISP, he's not going to know whether this is done for a reason or whether it's load sharing or anything. So he's just going to take all this subdivided address space and send it off into the internet. And then you get Jeff Houston and the CIDR report coming chasing you saying, what you doing? Okay? So, well, Jeff doesn't do that, but so the no export community is actually very useful for this. It means that you can still send your /16 announcement to your upstream ISP, and the prefixes you want, or the subdivided address space that you need for load sharing purpose, you can tag with a no export community and send to your upstream. The upstream sees this no export community. Now he'll send it to all his iBGP neighbors, but whenever it gets to any border router that's talking to other ISPs, the no export community tag prefixes will be automatically dropped. As I say, on router G at the end there, the only one that's announced out is 170.10/16. So you can chop your address space into pieces to do the load sharing between you and your neighbor, but you don't end up filling the internet routing table full of this shrapnel. Okay. Another one I thought was worthwhile explaining. I tried to make the picture as simple as possible, but I think I've ended up making it more complicated than it needs to be. This is a recent one. It's to try and make, I suppose, again, load sharing a little bit easier so that the core of the internet is not filled up with the results of load sharing. For example, you've got an ISP at router A, he's got several upstreams, and he's got to subdivide the address space to try and make his multi-homing load sharing work properly. So you've got 3 upstreams at router D, C, and B. So he sends 170.10/16 to each of his upstreams, as you do, and then he sends sub-prefixes of that address block to his upstreams also to try and get his load sharing to work. And he tags those with the no peer community. Now remember, no peer means the prefix will not be sent to bilateral peers. It will be sent to upstreams, but not bilateral peers. So it gets to router D. Well, D peers with C and D peers with E. So D won't send that sub-prefix to C and E. Likewise with router C. Go to router B. Well, router B has only got an upstream, so he'll still send the sub-prefix that he's learned from router A, and he'll maintain the no peer community and send it off to router E. When it gets to router E says, well, C and D are peers of mine, so I'm not going to send this no peer tagged community prefix to my peers. I mean, if E had any upstream, then he'll still send the sub-prefix onwards that way. Okay, so that's the purpose of the no peer community, to try and let ISPs towards the edge of the network do the traffic engineering for load sharing without actually filling up the core of the internet routing table full of this small bits of networks that aren't really useful for anything else. Okay, implementation details of community. Well, community is an optional attribute. And again, if you're using different vendor equipment in your network, you've got to be careful, make sure that you understand what each one does. Some implementations send communities to IBGP peers by default, some don't. Some send communities to EBGP peers by default, others don't. So if you're careless with this, then you can end up with community confusion. I've seen many cases where ISPs have sent no export community to their upstream ISP because they're using vendor A equipment, and upstream is using vendor B equipment, which ignores communities altogether unless you actually tell the BGP configuration to expect communities. And then they don't understand why all the /24 prefixes are spread around the internet when they're actually only using them for multi-homing. So you need consistent policy within your own networks. If you're going to use them between you and your upstream ISP, have a chat to your upstream ISP and your peer ISP to make sure that what you use is what they understand. Otherwise, you might end up with a bit of confusion. Okay, I've talked about the BGP path selection algorithm. So, what is it? Well, it's how the router decides what's the best path. I mean, BGP just sends information, reachability information, but as soon as you've got more than one BGP neighbor, you have possibility of more than one path somewhere. And many ISPs have huge numbers of BGP neighbors, so they can end up with huge numbers of paths to get to the same destination. So before we enter the path selection algorithm, which is how BGP decides where to go, first thing we look at is, well, paths with no route to the next hop. If you have no route to the next hop, there's no point even considering this path. Think back to the next hop attribute that I was talking about a few slides ago. The next hop must be reachable, otherwise your prefix will get tossed away at this stage of the path selection algorithm. Also exclude any paths where the AS path attribute contains an AS loop. So if you see your AS in the AS path behind other ASs, then you can throw away that one as well. So multiple paths to the same destination with the same local preference. Local preference is basically the first one. You compare local preferences between the paths. Highest local preference wins. If the paths have the same local preference, then we go into this BGP path selection algorithm. Okay, so highest local preference. Step 2 is the shortest AS path. An AS set, which I haven't talked about, but it's just a group of ASs responsible for originating a prefix. That counts as one AS hop, because it's really just a group of ASs acting as one. Then I've mentioned the origin code before. The lowest origin code wins. So IGP is more important than EGP, more important than complete. Or if I translate into modern language, BGP is more important than EGP, which nobody uses, which is more important than something that's come from another routing protocol. If it's still the same, then we compare MEDs. MED is only compared if the paths are from the same AS, module any vendor knobs that you might have. If the routes have no MED set at all, then they're considered to have an MED of 0. Okay. If it's still all the same, then you prefer eBGP path over iBGP path. In other words, we try and take the nearest external exit to our network. Okay, so if you get one path that's basically heard externally, the other one's heard from an iBGP router, you go out. Preferred path with the lowest IGP metric to the next hop. So in other words, if there's no external from the previous step, they're both iBGP paths, pick the one with the highest bandwidth, because lowest IGP metric generally means highest bandwidth. And if it's still the same, then we take the lowest BGP speaker router ID, and if they're the same, then we pick the lowest peer address. And IP addresses are unique, so this has to work. Okay, that's the final ultimate thing. As for recommendations, I generally don't like going much further beyond the IGP metric point, or even the eBGP path over iBGP path. I like to try and keep control over what's happening in my network using local preference. I don't want unpredictable stuff coming in from outside from my neighbors. Right? I don't want other ISPs to determine my own routing policy. So you want to try and have the router avoid going too far down this path selection process. You definitely don't want it to get into the last two, when that's just danger. You have no idea what's going to happen there. You could reboot a router, you get a different router ID, and suddenly your whole routing policy is completely messed up. So you want to try and avoid the last two steps. In multi-vendor environments, well, make sure the path selection processes are understood for each brand of equipment. Yes, they can be different. They all have slightly different implementations, extra steps, extra features, and so forth. So if you're using multiple vendors in your network, try and use all the knobs that they kindly provide you to make sure the path selection is actually going to do the same thing. Otherwise, you might end up with routing loops or even more interesting features. Okay, applying policy. Well, why? Policy is applied to influence BGP path selection by setting the attributes. That's generally why you want to try and apply policy, so that you want the router to make, I suppose, pick different paths over what it would normally do. It's also there to determine which prefixes are announced or blocked. You may have a private relationship between you and another ISP that you don't want the whole wide world to know about, so you use policy for that. You can use policies to determine which AS paths are preferred, permitted, or denied. You may get wonderful transit through one ISP, even though the path through another ISP might be better. So you load or you set BGP policy so you get transit through the nicest connection. Okay, the decisions are generally based on prefix, AS path, and community. Those are the three features that generally are used for applying BGP policies. Tools that you've got, well, there's prefix manipulation, filtering, you can play around with AS paths, various things there, and there's lots of things you can do with communities also. Most BGP implementations have some sort of policy language, which can do various match set constructs on attributes of chosen BGP routes. So that's, whichever one you look at, you find there's some pretty powerful tools that will let you do a lot of things that you probably want to do, probably also things you don't want to do, and maybe some things that you can't, and so forth. Also, just a quick by-the-by while we're on this, have a look at some of the extensions in BGP, or call them BGP capabilities. These are documented in RFC 2842. BGP originally started off just being for IPv4 unicast. But there are a lot of other things that have been added and so forth in recent times that have come through this BGP capability extension described in this RFC. Capabilities 0 to 63 are assigned by the IANA, it's by IETF consensus. The next 64 on a first-come, first-served basis, and the final 128 are vendor-specific. The current capabilities that we've got, well, if the BGP implementation supports multi-protocol extensions for BGP, then it will advertise the capability that it has a capability code 1, and that will let you know that the neighbor will support multi-protocol BGP. If you support route refresh, which I'm going to come talk about in a second, that's capability 2. 3 hasn't reached RFC yet, it's still an internet draft. 4 is an RFC, but I'm not aware, I haven't seen anybody actually using it yet. And then 64 through 67, again, are still in the development process. The URL at the bottom has the current list of BGP capability codes. Multi-protocol extensions, well, this is a whole different world. People often ask me, oh, well, can you not talk about BGP doing this, that, and the next thing? It's like, it's enough trying to do this BGP tutorial, which is an introduction, without getting lost in the V4 multicast, or V6, or V6 multicast, or even the whole big VPN world for BGP. I mean, those are other tutorials, probably quite substantial ones as well. But the multi-protocol extensions to BGP will let us do things like VPNs and multicast and so forth. Route refresh is coming up, and as I said, others are still in development, basically, or at least not deployed very much. Right. So, scaling BGP. So I mentioned 1 or 2 little problems just going through the introductory part for BGP. First one, how do we scale the iBGP mesh beyond a few peers? Well, remember I said iBGP, the routers have to be fully meshed, because we only take prefixes we've learned externally, or ones we've injected into the routing table ourselves. So what happens, this is fine and easy for maybe 5 or 10 routers. What happens with 50 routers, 100, 200, 500, 1,000? How do you run a full BGP mesh that size? How do you implement new policy without causing flaps and route churning? And I talked a little bit about this when I mentioned communities and how we found great use of them way back when they were first introduced. Well, there are ways now that BGP has, or implementations have, to implement new policy in BGP without tearing down the whole session. And of course, how do you go about keeping the network stable, scalable, as well as simple? So we've got these 4 things which we're going to have a look at, the 4 techniques. First one is route refresh, which I just mentioned. The problem is basically this. A hard BGP reset is required after every policy change. Okay? And this is required because the router doesn't store the prefixes that are rejected by the policy. If you've got filters on your BGP session, prefixes come in from your neighbor, they don't match your filters, or they're blocked by your filters, your router throws away those updates, that information, it throws it all away. So if you change your policy, and your policy would now allow those updates, well, your router can't just sort of go rummaging around in its bin to try and find what updates are received in the last day, week, month, or year. Okay, you need some mechanism to get your neighbor to send all the updates through it again. And what we used to do in the old days was, well, we just shut down the BGP session, bring it back up again, and then all the prefixes would come in from the neighbor, and then you could implement your new policy. Now, when the internet was not really used by very many people and not used very seriously for business, that didn't really matter. We could reset a BGP session in the middle of the day, and well, if a customer complained, well, say, oh, well, internet's still being developed and so forth. You could fudge it like that, but nowadays you definitely can't. Okay, so hard BGP peer reset tears down the BGP peering. That can be 1, 2, 3, 5, 10, 15 minutes to restore it, depending on the situation. Takes CPU on the router, but worst of all, it severely disrupts connectivity for all the networks. If it's a major transit point providing connectivity between many different networks, people are working away there, and suddenly the connection goes, and it takes 5 or 10 minutes to come back. If you're in the middle of a telephone conversation or watching TV, and that disappears for 5 or 10 minutes, well, you get a bit upset, especially if it's sort of the middle of the match, or you just missed a touchdown or something like that, because the television transmitter broke or something, just for that critical thing. It's the same thing in the internet. You can't have a disconnect in the middle of the day like that. You could do what we did and do this during the maintenance period, but having to reset BGP sessions during the maintenance period when customers wanted it done 4 days ago for the new policy, that's not very customer friendly either. So the solution for this was route refresh. Okay. So it facilitates non-disruptive policy changes. For most implementation, no configuration is needed. And it's actually automatically negotiated at the time the peer is established. When you bring up the BGP session, the router will say, I can support capability, whatever it was, 2, I think, for route refresh. And the other neighbor says, ooh, can you? Well, I can support capability 2 as well. Isn't that amazing? And so they exchange the capability that they can support route refresh, and from then on you can use the router configuration commands to do what's basically a soft reset on the BGP session. You send a route refresh request, your neighbor says, okay, he wants to refresh the prefixes he's heard from me, so the neighboring router just sends all the updates, again, without tearing down the BGP session. Okay, it doesn't need any extra memory in the router, it doesn't really take any extra resources at all. And it's an amazingly simple solution to what's been a fairly serious problem in the early days of the internet. So RFC 2918 describes all that, and as far as I'm aware, virtually all implementations now support route refresh. And if you're not using route refresh, if you're still doing the hard reset of BGP, I'd strongly encourage you to move over to using route refresh, because hard reset of BGP, quite frankly, is equivalent to rebooting a router. That's how I teach it now in all the workshops and so forth, and I do get annoyed with the class when I see all these BGP sessions being torn down, hard torn down. There's absolutely no need for it at all. And even on the internet today, looking around, I find virtually no peering sessions of all the networks I have access to. Virtually nobody cannot support the route refresh thing, so there's virtually no excuse for not using it. Of course, if it's not supported, you find that a lot of implementations will have some sort of workaround. Some implementations will store a lot of the updates that they received before the BGP policy was applied. Now that will take more memory, but that could be a useful workaround as well. Okay, so have a look at the implementation and try and use this non-disruptive route refresh facility. Flap damping. Okay, route flap, that's basically the going up and down of a path or a change in an attribute. So if you withdraw a prefix and then re-announce it, that's basically a flap. Okay. Or you change an attribute, so it could be some feature of the or attribute of the prefix is changed for some reason, that is also counted as a flap. Notice that if you reset the BGP session with a neighbor, that is not counted as a flap. Okay, it's only if you get the withdraw message followed by an update message in the BGP session that it's actually a flap. The whole point of flap damping is to try and reduce the scope of this, ripple. I mean, it starts off as a ripple in your local network because you're only withdrawing one prefix. But if you've been watching any of the NANOG presentations or any of the other major conferences, you see that this ripple in your local network becomes a tidal wave on the other side of the network. And a lot of ISPs, certainly when there were weedier CPUs in the internet routers, got quite upset that the amount of CPU that these route flaps are actually taking. So flap damping was one of the solutions of this. So if a prefix flapped a lot, it would be suppressed and basically told to go away until it sorted itself out and stopped flapping. Whereas any prefixes that were stable were allowed through. Okay? So the requirements were basically fast convergence for normal route changes, use history to predict the future, suppress oscillating routes, and advertise stable routes, as I just said. If you want to read about it, it's a very good write-up in RFC 2439. But the operation is simply this. You add a penalty for each flap. The change in attribute can also be penalized. You exponentially decay this penalty. You can set a half-life time, which will determine the decay rate. Penalty goes above a certain suppress limit. You don't advertise the prefix to BGP peers. As soon as the penalty goes below a reuse limit, you then re-advertise the prefix to a BGP peer. So it's quite a simple thing. Flap too much, penalty gets too big, you're off. As soon as you can sort yourself out, you're stable again, the penalty will exponentially reduce to a certain threshold that you set, and then once you've reached the threshold, all is okay, and you re-announce the prefix. Okay, so the graph looks like this, or the picture looks like this. If you plot penalty value against time, the network's announced, it flaps for the first 3 times, hits a penalty value, it's above a suppressed limit, and the prefix is now no longer advertised from about time 6 through to time 22. Carries on flapping, it flaps to about time 13. The distant ISP figures out what's gone wrong, or the circuit has stopped being broken, or whatever has been done to fix things. And then we have stable announcement by the remote network. The penalty exponentially decays. It will reach the reuse limit, and at about time 22, 23, and then the prefix gets re-announced. Okay? Notice that for just a few flaps is quite a long suppress time. Okay, and that was one of the issues I'm going to talk about in a bit, that when flap damping first appeared, the vendor defaults were actually very aggressive, probably more aggressive than what the ISPs wanted. And because you could flap 2-3 times and you'd be gone for an hour, which is like not too friendly. You know, if you rebooted the router a couple of times, you could end up with a situation like this elsewhere in the internet. So it's only applied to inbound announcements from eBGP peers. And it's only applied to the path that is flapping. And some people won't touch flap damping because they think, oh, well, if the prefix flaps, then everything's suppressed. Okay, it's only applied to the inbound announcement from eBGP peers and only applied to the path in question. And you've got various controls. You can control the half-life time, the reuse limit, the suppress limit, and the maximum suppress time. Okay, all these are changeable from vendor defaults. Okay, the various ways that you can implement flap damping, but European and US ISPs got together a few years back. It must be about 7 or 8 years ago now was the first incarnation of this particular recommendation. Probably must be about that. Where we considered that the vendor defaults were too aggressive, and so we came up with something that allowed more flaps and wasn't so harsh. So, and these particular recommendations, the RIPE 229 recommendations, hit /24 is very hard. I think they still stay with something like 60 minutes suppress time, whereas 22s and 23s weren't hit quite so hard. And the various networks like the root servers and so forth had no flap damping applied against them at all. So if you're going to implement flap damping on your network, I would rather you don't go and implement vendor defaults without thinking about it at least. Have a look at the recommendations for ISPs there in the RIPE document. Now, there's been some discussion about those within the last year or so as well, and some people saying that they are too aggressive also. So it's very much a case of, well, I think it's still being discussed. It's probably the polite way to leave it. Okay, route reflectors and confederations. So here we've got a full IBGP mesh. We've got 13 routers, and that means we've got 78 IBGP sessions. What happens when we have 1,000 routers? Now, maybe 10 years ago that would be a ridiculous concept for most ISPs, but these days it's definitely not. It's a very, very real thing, and there are many networks that have more than 1,000 routers in them. So how do you avoid having less than nearly 500,000 IBGP sessions? Well, I suppose you could try configuring them all, but I wouldn't want to guarantee any operation at all. Better solutions are to use either a route reflector or confederation. I mean, there were two solutions. Confederation came along first, and I think route reflector came along in memory about 6 months later on. But they came roughly at the same time. Okay, so that's how you avoid basically an n-squared problem with trying to scale IBGP. How does the route reflector work? Well, standard IBGP, remember, our IBGP speaker, if we hear a prefix from the outside, we only send it to our immediate IBGP neighbors. So router B would send the prefix to router A and to router C, as per the black lines on the diagram there. If we make router A a route reflector, it'll take the prefix that it learns from router B and send it on to router C. So we're now saying that we're changing IBGP slightly, so any IBGP prefixes we learn, we send them on to other IBGP speakers. That's all a route reflector does. It breaks one of the rules of IBGP. You can take prefixes from other IBGP speakers and send them onwards. And it's as simple as that. There are a few more rules to go with it. You can't just break that bit of IBGP and carry on regardless. A few more rules that go with it. Okay, a route reflector will receive a path from a client and from a non-client. It will pick the best path. If the best path is from a client, it will reflect it to other clients and to non-clients. If the best path is from a non-client, it will send it to clients only. Right, so a route reflector has what non-clients are just normal BGP speakers, and then it will have clients, which are these special routers that only speak to reflectors. So your network could look something like having the diagram there. Rather than trying to do a full mesh of the 12 routers in the picture, we set up the core of the network. Core routers are A, B, and C to be route reflectors, and then the routers at the edge we set up as the clients. And router A only talks IBGP with the clients at the top there, and IBGP with router B and C. So the red lines there are basically the IBGP sessions. Okay. So router A has gone down from having 11 potential IBGP neighbors down to having what? 1, 2, 3, 4, 5. Whereas the routers at the edge, the clients have only got one neighbor rather than 11 neighbors. And that's the way we scale the IBGP mesh. So if a prefix comes in from a client, it'll go to, well, say router A. Comes from the client to the top, it'll go to router A. Router A will take that prefix, send it to the other clients, and send it on to router B and router C. Router B hears a prefix coming from router A. It'll only pass it on to its clients at the bottom there. It won't pass it on to router C. Okay, so we maintain the IBGP, normal IBGP rules for routers A, B, and C, and we add these special features for the clients. And this scales. It's described in RFC 2796. I think that's being, well, I've just noticed there's an internet draft that's updating RFC 2796 on the go at the moment, so that's the current status of that. For scaling route reflectors, I've no idea how big this can scale. I've seen some huge networks that are using 2, 3, 4 layers of route reflectors quite effectively. Okay, I don't think there's any known scalability limit of it. Most people will deploy it by dividing the backbone into multiple clusters. You've got a core network, there you maintain your full IBGP mesh, and then say each point of presence, you'd set up a route reflector, and all the routers on the POP would be the clients. Okay, so you keep the route reflectors fully meshed. You can fully mesh the clients if you want to. Some people have route reflector clusters that cover a wide geographical area, and they find it more useful to actually fully mesh those for various topology reasons. But I generally don't like fully meshing the clients. There's generally no need to do this, to just rely on the route reflector in the middle. Don't touch your IGP. And some people try and head off and redeploy how their IGP is done. There's no need to do that. Just don't touch your IGP. It'll work fine as it is. There are two new BGP attributes. There's the originator ID and the cluster list attribute. Originator ID is basically got the router ID of the originator of the route in the local AS. So that's created by the route reflector. And the cluster list is a bit like the AS path. The cluster list has a list of route reflectors that the prefix has gone through. Okay. The thing to note about the cluster ID is some people will try and come up with some wonderful naming scheme for the cluster ID for this IP address that goes in the cluster list. Some people do it and they manage it very well because they have a well-documented process. But in a lot of cases, the router ID is set automatically by the router in any case, or you set it for your BGP session. So it's trying to play around with a cluster ID is generally a very dangerous process unless you really know what you're doing. So watch how you handle the cluster list. Most implementation defaults work just fine. Now, multiple route reflectors can be configured for the same cluster. I suppose in theory that all works quite well, and I've seen implementations where that works quite nicely, but it's really, really not to be advised. I mean, I've come across more cases where people have really tied themselves up in huge knots. I've ended up with black holes in the network, routing loops, and other disasters. If you've seen the BGP troubleshooting tutorial that I sometimes do, there's some examples in there of how you can really get yourself messed up badly if you use multiple route reflectors in a cluster. Okay, so the reason is that all route reflectors in the cluster must have the same cluster ID. Otherwise, it is a different cluster. Now, a router can be a client of route reflectors in different clusters. Okay, can be a client in different clusters. There's no problem with doing that. I think in the early implementations, there were probably some issues when this first came out. But most ISPs will now set up, say they've got two core routers in a POP. One will be a route reflector for one cluster, one will be the route reflector for the other cluster, and then all the routers in that POP will then talk iBGP with both route reflectors, and that works just fine. You need to do maintenance on one router, the other router, one route reflector, the other route reflector in the POP carries on providing all the routing information. So I've tried to draw it in a picture, and it's again, it's rather messy, but I think you get the general idea. If you look at POP 1, you see the red lines, that's cluster number 2, and the green lines are cluster number 1. Okay, so you've got the point of presence, you've got two basically overlaid route reflector clusters. And then the 6 routers in the middle there, those are just the full mesh iBGP as normal. So that's the way that ISPs tend to deploy it, rather than looking at old documentation which says the correct way to do it is to configure the cluster ID to be the same and have two routers as the route reflector in the core of the network. Okay, where to place the route reflectors? Always follow the physical topology. That's kind of important. You know where your backbone circuits are, you know where your POPs are. If you're following what I'm saying, your backbone is carry on with that being fully meshed, build the route reflectors within your point of presence. You won't go wrong. Your point of presence is generally an Ethernet or some similar medium. Things aren't going to go wrong in there. But I mean, again, I've seen route reflector deployments that go over whole states. And I'm not talking about the US, I'm talking about other countries. They're huge. And there's no physical, the physical network between a client and the route reflector goes through other clients, or through even other route reflectors in other clusters. It's really an awful mess. And anything goes wrong in the network, the routing loops and black holes that ended up were just, amazing. So always follow the physical topology, you won't go wrong. So typical ISP network might be that the POP has two core routers, as I said. The core routers are the route reflectors for the POP, and you have two overlaid clusters. That's a very common situation. Core routers are fully meshed iBGP. You create further hierarchy if the core mesh is too big, split the backbone into regions, and so on and so forth. How to migrate there? Well, you can do what I did about 8-9 years ago when these first appeared. Just do it in the maintenance slot. It took me 2 hours to do about 60 routers. It worked pretty well. I wouldn't recommend that to anybody else. So trying to tell everybody to take things gently. So you do one part of the network at a time, get comfortable with the migration, how the iBGP is all working, then next maintenance slot, go and do the next part of the network at a time. So a picture could be like this. Pick on one part, migrate it first, get comfortable with it, rip out the old iBGP sessions you don't need. Once you've run it for a week or so, you see how it works, then you move on to the next bit of the network. So nice, easy, gentle migration. And just before the break, I'll just zip through BGP confederations. Confederations are a different approach to it. What they do is they try and take your autonomous system and split it up into lots of small networks. Okay? So rather than using the route reflector cluster idea, you're splitting all these chunks of your network up into, I suppose, identifiable pieces. So one POP might be one autonomous system, another POP might be another autonomous system, and you split your network up into a large number of what are called sub-ASs, or sub-autonomous systems. Okay, so we're using eBGP between these sub-ASs, but it's not quite eBGP because you keep some iBGP information there. You preserve the next hop, for example, across the sub-AS. You preserve local pref and med, which you don't do in eBGP at all. You don't touch your IGP. Again, it's described RFC 3065. And again, I think I've seen there's a draft which is updating this RFC currently in the works. Now, you're still visible to the outside world as a single AS, so your AS number doesn't change. The way you actually deploy this is you have your own AS number, but you split your internal network into all these sub-ASs, and you use private ASs for this. Okay, there are 1,023 private ASs, so it should give you enough scope to subdivide your network into lots of pieces. This single AS is usually called a confederation identifier rather than an AS number, because you're using AS numbers inside your networks, just not to confuse. Okay, the iBGP speakers in each sub-AS are fully meshed, or you can use a route reflector within the sub-AS. I mean, it's up to you. The total number of neighbors is reduced by limiting the full mesh requirement to only the peers in the sub-AS. So that's how we reduce the number of iBGP neighbors across the entire confederation. Okay, you're sort of chopping it up into smaller pieces. So the picture could look like that. I mean, AS200 is your network as it was. You used to have a full mesh iBGP across AS200. You've now split it up into three sub-ASs, 65530, 531, and 532. They will talk eBGP with each other, and then you run iBGP inside. But the eBGP they talk maintains the next hop and med and local preference as it would do for iBGP. So some people call it EIBGP, just to add further confusion with the E's and the I's. You've also got this AS sequence. I mean, the AS path is kind of used by confederations. For example, 180.10/16 comes in from AS200 at router A. From router B, if we look at router C, we see 65002 in brackets in the AS path. And that number in brackets tells us that, well, this is transited confederation sub-AS 65002. So within the confederation, we see these sub-ASs in the AS path. But when we pop out the other side at router H, say we go to the neighboring network, we just see that it's AS100. That's all that's in the AS path. So the confederation sub-ASs are taken out of the AS path, and to the outside world, it just looks like AS100. So nobody can tell that you're running a confederation inside your network. Okay, route propagation decisions, the same as with normal BGP. So in other words, prefixes go from peer in the same AS only go to external peers. From external peers, they go to all neighbors. So that's pretty much the same with normal BGP. External peers refers to peers that are outside the confederation and peers that are in a different sub-AS. And as I said before, preserve local pref, med, and next hop. Comparing them, people always ask me, well, what should I use, route reflectors or confederations? Well, if you've been born and brought up on confederations, you're always going to use confederations because you're very comfortable with them. It's a bit like whether to use ISIS or OSPF. If you always use ISIS, you're always going to use that. Confederations, they scale pretty much as well as route reflectors do. You've got all the same multi-level hierarchy, you've got the same policy control. The major difference is migration complexity. Okay. Route reflector, you can more or less migrate to a route reflector in your sleep. It is very, very simple. Whereas migrating to confederation, you've got to do in a big hit. You've got to renumber the BGP AS number on your BGP session. You've got to set up all your BGPs and so forth. It can be quite a hard migration task. If you're going to deploy from day one, well, to be honest, most service provider, new service provider networks are using route reflectors now, simply because they're easier to manage and maintain. It's not to say that people aren't still using or deciding to go with confederations from the start. Some are, but I generally find it's more because the engineers working there comfortable with using confederations from previous employment. So that's an attempt to try and summarize what I think. I generally think route reflectors scale better. Then again, as I say, you can use route reflectors within confederations if you're worried about that. More points about confederations. It can be used to ease absorbing other ISPs into your ISP. So if you're on the acquisition trail or buying up assets of ISPs that have passed away, confederations are quite useful to have because you just make their AS a sub-AS of your confederation. But then again, some implementations have got this AS masquerading feature which will let you absorb them into your network also. And of course, as I said, you can use route reflectors within the confederation sub-AS to reduce the sub-AS by BGP mesh. Okay, so those are the 3 techniques or 4 techniques, depending how you count them, that are very important for scaling BGP. I put these into an introductory type presentation because I really want people to start using these from day one. Because trying to migrate to this when you start off building a network, after you've built a network, it's just hard. It's unnecessary work. If you can think about this from the start, then you have less to worry about when you really should be concentrating on getting more customers for your network. So I'm going to pause here for half an hour, and then the second part will be on, well, basically more on communities and then looking at some of the issues faced for deploying BGP in an ISP network. So thank you for your attention. If you have any questions now or during the break or later, feel free. Thank you.